Right. Let's unpack this.
Hmm.
Today, we're diving into something that honestly feels like it's straight out of science fiction. But the sources we've pulled together, they show it's becoming, well, administrative reality.
Yeah.
Very quickly.
Yeah, it's quite something. We're tracing these really intense lines of convergence. You've got digital infrastructure, the global economy, and then the sort of final frontier,
Yeah.
human biology itself.
Right. And our job today really is to synthesize the key stuff from a huge stack of material. We've got ILE standards, specialized stuff,
Hmm.
NIH-funded research, cutting-edge industry white papers, too. The mission, let's call it, is to show you, the listener, the map.
Yeah, the map of where this is heading, a future where connectivity isn't just, around us, but where the human body is actually designed to be an active, integrated piece of the network.
The scope is just, it's dizzying when you put it all together. We're connecting dots between things like the Department of Transportation's V2X, vehicle to everything.
Right. We do it.
Cyber-physical systems expanding everywhere. And then there's this confirmed government push, digital IDs mandated by January 1st, 2026.
And that timeline is pretty aggressive.
It is, and it all seems interwoven with this huge financial push driving healthcare towards what they're calling Healthcare 4.0.
Absolutely. And I think what's really crucial to get right up front is this shift in perspective. Think about smart home automation, right? The system's letting you control your lights or thermostat remotely.
Yeah, sure.
The basic assumption there is that the people inside that home are also part of the network being managed. The sources are clear if the IoT system is optimizing the home environment.
Then the human is just, well, in the mix, as they say, part of the system.
Exactly. Part of the system being optimized.
Okay, so let's start with the bedrock, the infrastructure itself. And that immediately raises this dependency crisis, doesn't it?
It really does. I mean, it's pretty well known that Amazon, through AWS, Amazon Web Services, controls maybe 30% of the public internet.
Which sounds like a lot, but maybe not a total monopoly.
Well, that 30% figure, it kind of masks the real severity of the entanglement, the vendor lock-in. Think about this. Google, Microsoft, Oracle, huge direct competitors.
Yeah.
They all depend on AWS for certain critical services. We saw reports that during a recent Amazon outage, parts of Google search went down. Microsoft Teams had issues.
Wow, competitors relying on each other's infrastructure like that.
And it gets, frankly, much worse when you look at essential public services. The sources pointed out, I think it was over 10 national health services in the UK. They were basically shut down during that same outage. Why? Because their core systems were running on Amazon's cloud.
So it's not theoretical risk, it's actual fragility already deployed.
Exactly. Deployed fragility. And we saw these specific anecdotes, too, showing how deep it goes in consumer light. People literally locked out of their smart homes because the servers failed.
Or you pay for that fancy security camera 24/7 recording.
Right.
But the cloud server crashes, and suddenly, poof, zero footage for that critical time. It's a loss of control, isn't it? Especially when health and safety depend on it.
A severe loss of control, tied to one single vendor.
And this centralization, it inevitably hits us in the wallet. There's this concept, economists are talking about the Amazon tax. Can you break that down?
Yeah, it's essentially market leverage driving up costs across the board. Take hospitals, for example. Many use software like Epic for electronic health records, right?
Common system.
But they often pay Amazon, AWS, to store those incredibly sensitive patient records in the cloud. Now, when Amazon decides to raise prices for storage or bandwidth, and they can because of their market position,
The hospital has to pay.
a hospital pays, and then they pass those costs along. It shows up in higher patient bills, higher insurance premiums for you, the listener.
So we're paying a hidden tax just for the centralization that makes the system work. But this reliance, it's not just about monthly cloud fees anymore, is it? It's changing how we even relate to physical things we buy.
Oh, absolutely. We're shifting hard from ownership to what's being called usership.
Usership.
Usership. It means you pay continuously to access features on stuff you've already bought, stuff you physically own.
Give us some examples.
They're everywhere.
Yeah.
The Oura Ring, right, costs a few $100. But then you need a monthly subscription to actually see and use the health data it collected from your body.
Right. I've seen that.
Or Toyota charging, what is it, $8 a month? Just for the ability to remotely start the car you already paid tens of thousands for. You buy the hardware, but you're essentially renting the functionality.
You own the metal, but not the features.
Precisely.
And this concentration of power, it's not just digital. You're seeing the same pattern in physical essentials, like the power grid itself.
It's a perfect parallel. Look at Blackstone, one of the world's biggest asset managers. They're actively buying up critical utility companies.
Like power plants.
Exactly.
Yeah.
We saw examples like Hilltop Energy Center, TX&M Energy, that one serves, I think, 800,000 people in New Mexico and Texas.
Okay.
Now, when these huge private equity firms take regulated public utilities private, they can potentially sidestep government oversight.
Meaning
Meaning a multi-trillion-dollar private company could potentially dictate electricity prices and supply for hundreds of thousands of Americans without the usual checks and balances.
Okay, I see the connection now. Control the physical power grid, like Blackstone is doing. That ensures the survival of the digital cloud grid, like Amazon's,
Right.
which then enables this biological grid. And that, I think, is where it gets really interesting.
Yeah, let's make that shift from the sort of economic cloud to the biological cloud. Healthcare 4.0.
So how does it work? How does a smart home connect to my health?
Well, the transition is designed to be seamless.
Yeah.
The sources are very clear that the architecture we just talked about for the smart home, the sensors, the connectivity standards,
Yeah.
it's being explicitly adapted and extended to integrate health services
Sure.
for what they call precision AI healthcare and remote patient monitoring.
RPM. Okay, sounds potentially beneficial for doctors managing patients remotely. But what's the actual tech? What's the mechanism making the patient into a network node?
Okay, the core mechanism here is the Wireless Body Area Network, WBAN.
WBAN.
And this isn't some niche experimental thing. It's a recognized global standard. IEEE 802.15.6 WBAN. It's the system specifically engineered to handle secure, high-volume collection of physiological data, your body's data.
And it works with wearables.
Wearables, yes,
Mhm.
but also temporary skin patches, implantables, even non-invasive sensors like specialized radar or light-based systems, anything that can capture biosignals.
So the system is just constantly scooping up my heart rate, blood pressure, maybe more. But hang on, if all this sensitive data is flying around wirelessly, how do they keep it secure? That seems critical.
It is critical, and this, I think, is one of the most startling findings in the material. To secure that patient-sensitive data transmitting over open wireless networks, they're developing authentication schemes that pull the security key directly from you.
Wait. Directly from me, like from my body. How does that work? Is my heartbeat literally the password?
Effectively, yes. That's what the research indicates. There's an authentication scheme described that uses cryptographic algorithms to extract what they call a binary biokey.
A biokey?
Yeah, described as an unpredictable variable length pattern. And it's extracted directly from the patient's real-time physiological signals, ECG, pulse rate variability, that sort of thing.
So my unique body signals are used to secure the network connection to my body.
That's exactly it. It confirms your own biological signature, becomes the basis for network security and authentication. Your physiology is the key.
That's profound. If the key is literally part of you, you can never really log off, can you?
That seems to be the implication.
Yeah.
And to make sure this highly personalized network is always on, always connected, they're building power redundancy right into the person, too.
How?
Through energy harvesting WBN concepts. The idea is to use the human body's own energy, thermal energy, kinetic energy, from movement to power the tiny sensors monitoring you.
So I power the sensors that monitor me.
It ensures system continuity. The patient isn't just the data source. In this model, you're potentially the power source as well.
Wow. Okay, this level of biointegration is intense. Which brings us to the underlying science, right? They need to understand the body's systems at an incredible level of detail, mapping the bioelectric reality.
Exactly, and the ambition here is vast. The sources highlight a major NIH-backed project, $14.2 million over 5 years, dedicated entirely to mapping something called interosception.
Interception, what is that?
It's often described as the body's hidden sixth sense. It's the brain's ability to sense internal bodily states, hunger, thirst, pain, your heartbeat's rhythm, even your immune system's activity level.
Things I don't consciously notice most of the time.
Precisely. Most of it happens below conscious awareness. It's essentially the body's internal operating system constantly talking to the brain.
And the NIH is spending over $14 million just to map this internal chatter. Why? Is it just scientific curiosity?
Not at all. The data strongly suggests that when this internal communication pathway breaks down, when interoceptive signals get disrupted or misinterpreted,
Yeah.
it's directly linked to some really severe conditions. We're talking autoimmune disorders like rheumatoid arthritis, chronic pain syndromes, hypertension, even neurodegenerative diseases like Alzheimer's or Parkinson's. Understanding the map is the first step toward intervening.
Intervention. Okay, that leads to this broader idea you mentioned, bioelectrical homeostasis.
Correct. It's a fundamental concept. The body needs a stable internal bioelectrical environment to function properly, to maintain health.
Like keeping the voltage steady?
Sort of, yeah. It's much more complex, but that's the gist. Now, the sources detail research looking into disrupting that electrical balance deliberately. For example, to selectively target and kill cancer cells.
Which sounds potentially amazing as therapy.
It does. Potentially revolutionary. But it highlights this incredibly sharp, double-edged sword. If you disturb the body's electrical stability, even slightly, whether intentionally for therapy or maybe accidentally through environmental factors or system malfunction, it can promote disease or even cause death if not managed with absolute pinpoint precision. We're talking about manipulating the body's entire electrical atlas.
Yeah.
It's delicate.
Extremely delicate. Now, that's intervention using electrical signals, but you mentioned the next step goes beyond electricity into actual chemistry. Molecular communication.
Yeah, it sounds like something from a sci-fi novel, but the research is there. We're talking about encoding digital information using the body's own internal fluids and pathways.
Like sending data through my bloodstream. How?
One mechanism explored is molecular communication via diffusion. Basically, using molecules moving through, say, blood vessels, not just to carry oxygen or nutrients, but to carry complex digital messages coded chemically.
Okay, my brain is stretching here. How do you send a digital 1 or 0 using molecules?
Well, one technique research, going back as far as 2014 actually, is called isomer-based molecule shift keying.
Isomer-based.
Isomers are molecules that have the exact same chemical formula, but different 3D shapes, different structures. The research showed that by releasing different types of isomers, different shapes, into a fluid medium like blood analog, you can encode binary data, zeros and ones. It's literally information transfer at the nanoscale, using the body's internal chemistry as the communication channel.
Okay. That level of control, it perfectly sets up the need for incredibly advanced computing systems to manage and interact with this bioelectric and molecular reality, which takes us to neuromorphic computing.
Exactly. And the quest for, well, true machine intelligence. The key early investment here was the DARPA-funded Moneta project back in 2010. The explicit goal was foundational: create a general-purpose intelligence by directly mimicking the processing architecture of the mammalian brain.
Not just faster calculations, but actual learning and adaptation like a brain.
That's the idea. And the hardware breakthrough that really enabled this shift away from traditional computer design was the memristor.
Memristor,
No.
developed by Hewlett-Packard.
That's right. Traditional computers, von Neumann architecture, they strictly separate processing the CPU and memory, RAM, storage.
Yeah.
Memristors are different. They function much more like biological synapses in the brain. They allow memory and processing to happen essentially simultaneously in the same physical location.
So it's faster and more efficient.
Dramatically so, especially for tasks involving learning and pattern recognition. It fundamentally changes how systems can adapt.
And this new approach, this brain-like computing, that's what they call wetware.
That's the term, yeah, wetware, where the software and the hardware are almost inextricable, blurring that line between the machine and, well, something more organic. The goal is to build systems that can handle ambiguity, improvise, learn on the fly, much like living organisms do.
And this drive for wetware for brain-like systems, it must lead to new ways of interfacing with biology itself.
It absolutely has. Look at very recent work, MIT, in 2023. They're developing nanoscale devices using metamaterials.
Metamaterials, these engineered materials with unnatural properties.
Exactly. And these nano-devices are designed to remotely monitor and even modulate biological systems. And, crucially, non-invasively. No surgery, no implants, no gene editing needed.
Non-invasive control. That seems like a huge leap. These are untethered, tiny devices potentially inside the body. What can they actually do?
Okay, according to the research, they can harvest energy from external fields like radio waves, so they don't need internal batteries.
Just self-powering.
Right. And they possess capabilities for internal analysis, sensing things locally, electrical stimulation, and perhaps the most striking capability,
Right.
wireless drug delivery.
Delivering drugs wirelessly inside the body to specific spots.
Down to single neuron precision is the claim, delivering a tiny payload, a therapeutic intervention to one specific target neuron, all controlled remotely.
Wow. Single neuron control. Remotely. That implies an almost unimaginable level of surveillance needed to operate such a system safely and effectively. How is that constant monitoring achieved if people aren't wearing sensors all the time?
Well, it seems to rely on several advanced non-wearable techniques that are already quite developed. One is visible light communication, VLC.
Using light for data?
Yeah, essentially turning any LED light source into a potential high-speed data network node that can also be used for positioning and tracking indoors. Another is sophisticated radar technology, specifically continuous human activity recognition radar, sometimes called simulator radar.
Radar, like the police use.
Similar underlying tech, but adapted. It's often used by law enforcement or defense for through-wall surveillance, but it can also be used to monitor fine-grained human activity.
Wait, so this kind of radar can track my tiny movements, maybe even my breathing or heart rate, just by being active in the room, without me wearing anything?
The capabilities described suggest exactly that. It confirms that constant non-physical, non-contact monitoring is entirely feasible. The environment itself, the room you're in, can become the sensor array.
Okay. Let's try and tie this all together. We've got the economic dependence on centralized digital infrastructure, the creation of a wireless body area network standard, the deep mapping of our internal bioelectrical systems, molecular communication potential, and now these non-invasive control and surveillance systems. What does it all mean when you put these pieces together?
I think when you synthesize these different sources, the standards documents, the research papers, the financial trends, the takeaway is pretty stark. This convergence, this merging of the economy, digital infrastructure, and human biology. It's not some distant future theory.
It's happening now.
It's a deployed system. It's supported by billions in investment, by internationally agreed upon standards like that WBAN spec, by established market share in cloud computing and healthcare tech. The whole framework is being built to treat the human body as, essentially, an addressable, programmable, integrated node in a global information grid.
And the technologies we discussed, memristors, metamaterials, molecular signaling, they aren't just lab curiosities. They're mature, they're designed to work together, they're incredibly interdependent.
Exactly. The future they seem to be building relies on controlling both the external factors, like the power grid, and the internal factors, like the bioelectrical stability of the individual.
And it seems like this system is being rolled out piece by piece, often without people fully realizing that their own physiology, their very biology, is being drafted into the machine.
That seems a fair assessment based on the trajectory outlined of these materials.
So the final provocative thought here. We saw that these biocyber systems are designed to use your own biological signals, your pulse, your ECG, your unique bioelectric field as the method for providing cybersecurity for the network itself.
Right. The body secures the connection to the body.
So if the system is fundamentally architected to secure its connection to your deepest physiological reality, it raises a really crucial question for you, the listener. When connectivity becomes this foundational, this intimate, how do you even begin to think about setting boundaries for your own digital twin? Where do you draw the line?
That's the question, isn't it? Where can you draw the line?